Hello everyone, in this video we're going to talk about some challenges in data science. This video it's going to be posted in both courses, in the data analytics course and also in the big data. Because it's not, when you're learning data science, it's not just about the tools like R, Python, Hadoop, like the software that you typically use in your analysis. It's also about the way in which you perform those analyses. So when we talk about data science, machine learning, we know that at the end, the idea most of the time, is to identify patterns, make predictive models. In general, we want to mimic the way in which humans identify such patterns. And even though our basic models are simple to understand, let me show you how complex it's our minds. So this is an example. Here we have two characters. Let me tell you that one of them, the name is Buba. B-U, B-U, Buba. I'm sorry, B-A, Buba. And the other one is Kiki. So I want you to pause the video just 10 seconds. I want you to tell me like which one is the first one. So this is the first character and the second one. So which one do you believe is Buba and which one do you think is Kiki? So just this is not about this question is not about like there is not like a right answer. It's about perception, right? So there is not like like I'm not trying to disguise something here. It's just like according to your perception, which of these two characters do you believe is Buba and which one is Kiki? So I'm gonna give you 5 seconds. You can pause the video. Okay, so I'm pretty sure that at least 90% of you will claim that the first one is Kiki and the second one is Buba. Well, I don't know the answer. It remains a mystery. We still don't know which one is Kiki and which one is Buba. But what I can tell is like at least 90% of like individuals will say that this one is Kiki, and 10% or less will say that this one is Buba. I have asked my students like why do they think that? Typically they say okay, this is Kiki because the letter K is sharp and like the character Buba, it has like a rounded shape and things like that. Well, that's just our mind identifying patterns because I believe this word Buba and Kiki, they do not exist, and even these two figures, they are like abstract figures, they do not exist. So this is just our minds connecting, some patterns, and this kind of like show how complex we are. So how can you model that? Like how can you model this capacity that we have to identify patterns in abstract figures and even abstract words? So it's interesting. I have performed this question, like to not just to English speakers, also to Spanish speakers, and even Arabic speakers. The conclusion is it's the same. So yeah, this shows how complex we are. Now let me show you two problems that when you're doing your analysis, you can make some wrong conclusions. Okay, so this is problem number 1. So it's like a case about Linda. She's 31 years old. She's single, outspoken, and very bright. She majored in philosophy, and as a student, she was deeply concerned with issues of discrimination and social justice. She also participated in anti-nuclear demonstrations. So, which of these two scenarios is more likely? A. Linda is a bank teller. B. Linda is a bank teller and is active in the feminist movement. Please take 30 seconds. You can pause the video and pick one of the two options. I'm going to give you just 10, but you can pause the video if you want. Alright, so typically what I have seen is like around 80% people will say that the correct answer is this one. This is what typically people will say, that Linda is a bank teller and is active in the feminist movement, and 20% or less than that will say that Linda is a bank teller, right? So let me tell you, in this one there is a correct answer. So here we have two events. So this is a Venn diagram. Maybe if you remember from your statistics class. If you don't remember, that's fine, don't worry. So this is the whole universe, and we have two events here. So the first event is Linda is a bank teller, and the second event is that she's active in the feminist movement. Now, when we talk about the probability of A, Linda is a bank teller, so that will be all of this, the circle, the whole circle, the complete circle, right? That's the probability that she's a bank teller. Now, when we talk about these two events, Linda is a bank teller and is active in a feminist movement, that's the intersection of A and B. So it's just the overlapping part here. So from the statistical point of view, from the numerical point of view, the correct answer is A, because it has a higher probability. Linda is a bank teller. So why people here typically will pick the wrong answer? That's because even though I'm pretty sure that if I ask you if you are subjective, you will say, no, I'm not subjective. I always, like make decisions based on facts and data. I know that. But to be honest, sometimes when we're given some context, that context will kind of like affect our judgment, and sometimes we go even against the numerical evidence, like in this case. So this problem, it's called the conjunction fallacy. The conjunction fallacy is when you think that the intersection of two events is more likely than a single event. That's not possible, because the conjunction, the intersection, is just one part of the events. So it's not possible that this probability is going to be higher or greater than one of the events. That's just not possible. Now, it's interesting because some of the people that typically use this problem, I remember one of them was telling that even though he knows the answer, still in his mind he believes like that B is correct, right? Because given the context, I mean, you don't imagine just Linda, like sitting there as a bank teller. You want to believe that she's more active, and that's why we go against the numerical evidence. Okay, so this is the conjunction fallacy. So you gotta be careful. That's what I show you. That's what I warn you, that you gotta double check your numbers, right, before you make a decision. So ensure that you're not making a wrong decision based on the context. Okay, so that was the conjunction fallacy. Let's move to a second problem. So in this one, this was an observational study. When we talk about observational study, that means that we didn't perform like an experiment. This is pretty much like you have a database and you use that data from the database. That's it. Okay, and the idea of the study was to check sex bias in the graduate admission for a university in the US. So there were some claims that maybe the admissions were more like, were biased. So this is the general information. So during the study period, there were 8,442 men applicants, 4,320 women applicants, right? They applied for the graduate school. Now, about for the men, 44% of the men were admitted, while 35% of the women were admitted. So just to give you a different perspective, so for every 100 men, on average 44 were admitted, and for every 100 women, 35 were admitted. So these probabilities are not affected by this number, like by the 8,400 or by the 4,300. So this is measured based, like, okay, how many men were admitted divided by the number of men admitted. So the final answer would not be affected by this difference. Now, my first question is, do you believe that just by checking these numbers, the 44% and the 35%, do you believe that there is a bias here just by checking at the numbers? So I'm going to give you some time to think about it. Well, maybe some of you will think, okay, the gap is not that big. So it's like 9 points, like 9 percentile points, like from 35 to 45%. But this is around like 20%, right? This difference is like 20-25%. So it's big, right? It's big. Possibly most of you will believe that there is some bias. But with this, like with these allegations, the university released more data. So instead of giving just the aggregated data like that you are looking right now, they provided more information. So the original gap was, the difference was like 9 points, right? So let's see the new data. So this information was released. So instead of giving the complete information, they say, okay, here's the data for the 6 largest departments in our university. So you can think of A as like, I don't know, like computer science, BA psychology, those are like different, big departments. So we have information for men and for women. Now, for the 6 departments, if you check the aggregated data, so 45% of the men were admitted, while 30% of the women were admitted. So the gap looks huge, even bigger than the previous slide. So maybe at this point you're thinking, oh no, maybe there is a point, right? There is some bias, there is something wrong in the process. So, but now let's check the detail. Let's check like every single row, each department, and let's see if we see some bias. Okay, so for department A, the first row, the number of men applicants was 825, and the admitted is 62%. In the case of women, the admitted is 82%. So in department A, for sure there was no bias, and actually, if there is some bias, it was in favor of women, right? Compared with this, if you check the percentage. So now if we check percentage for department B, we have a similar story. For men, we have 63% admitted, but for women, 68%, right? Again, more like a higher probability for women. In the case of department C, there was a small difference, but in this case, it was in favor of men. Like for each 100 men, that is around 37 were admitted, and the number was lower for the women, right? So maybe here, okay, you might think, okay, that maybe there's a bias, or there was just a small difference. I mean, in general, it will be difficult that you will get, like exactly the same percentage. That will be difficult in general. Okay, for department D, we have similar story compared to A and B. So women had a higher acceptance rate. In E, it was more in favor of men, and in F, they were similar, or if you want to say that for women it was a little bit higher. So now if you check the trend here, please notice that out of the 6 departments, in 4 of them, women had a higher acceptance rate. So at this point you think, okay, that for sure there was no bias, because yeah, in most of the departments, women had a higher acceptance rate. But the problem is, like in the aggregated data, you don't see that. Actually, you see the opposite, right? So what is the lesson here? What's the lesson here? You gotta be careful with aggregated data, because I know sometimes you want to see the big picture, but if you don't see the details, maybe you will misjudge the situation and you will make a wrong decision, because here the aggregated data is showing something different than the original data, right? Now, why it's happening in this specific problem? Now, if you notice, for example, most of men, they apply to department A. Did you see? Like that was the department with the highest number of men applicants, right? The department A. And the department had a really high admission rate. The acceptance rate was high for that department compared to the other departments. Now in the case of women, that was not the case. If you notice, women, they apply to a department with a smaller acceptance rate. I mean, most of the women applied to department C, and the acceptance rate was only 34% compared to the 62%. So that was the issue here. At that moment, for that specific university, I don't know the details why, but women were applying to like more difficult departments, or departments with a smaller acceptance rate. So that's why that affected the aggregated data, right? So overall, this problem is called the Simpson's paradox. So the Simpson's paradox is when your data shows like there is a pattern in the aggregated data, but when you check the disaggregated data, you will notice that the pattern it's the opposite, right? It disappears, it reverses. So you gotta be careful because you can make a wrong conclusion based on the aggregated data. This is not going to happen always. So be careful. But the Simpson pattern is just a warning to show you that do not trust just the aggregated data. You need to look the details before you make a decision, right? So that's the whole idea of this concept. So with this, like small problems, I just want to show you, like it's like a warning. I want you to be aware that data science is not just about creating models, finding patterns. It's also about making decisions. It's also about analyzing data. In order to do so, you gotta know that sometimes you can make mistakes. So you have to get more tools when you're making these decisions, and that's why I want to present in these videos some of the common problems. So that's why I presented the conjunction problem and the Simpson paradox. So in the upcoming weeks, I will try to post at least every other week one video, not just about tools, also including some of this type of discussions, errors and some tips for decision making during your data science analysis. Okay, I will see you in the next video.